Hello again. Now we're going to take a look at problem number 7 from the most recent exam. The International Space Agency has landed a robot on another planet. The probe launches a baseball upward at 147 feet per second from its ground level ejection port. How long will it take the baseball to smack back into the surface of the planet? The gravity on that planet is negative 96 feet per second squared. That changes our equations. Now, once again, as I said in the last problem, we're just going to go ahead and take these equations on faith for now. You don't get to learn precisely how they're created until calculus. So for now, we're just going to take them as given. So, once again, as before, as every single time, you guys are probably really sick of hearing me say this for now, but what's the first thing we have to do? We have to write down what we know. We absolutely have to do that. It'll keep us organized, keep us from getting confused. So, first things first, 147 feet per second initial velocity. That's simple enough. Now the initial height, the wording was a little bit odd. I did that on purpose because I want you guys to be able to pull data out from different kinds of words. So it was fired from the ground level ejection port. The ejection port is at ground level. Well, we know what ground level means. It means that the initial height is 0. How long will it take the baseball to smack back into the surface? Now again, I had some students again trying to plug in velocity equals 0 for some reason. Maybe because that's how we did it in problem 5. But again, if you try to pretend that all of these problems are going to be solved in exactly the same way, you're going to get the first one right and the rest of them wrong. So, what do we know? Smack back into the ground, or into the surface of the planet. At the moment that we're discussing, the moment that we're trying to work with, the ball has gone up, it has come down, it has hit the planet again, its height is 0. Once you have these three values, the problem becomes very, very similar to a problem that we've already done. Let's go ahead and plug what we have into the appropriate equation, and the appropriate equation being the equation that we have enough pieces for so that we can solve. We have height, we have initial height, we have initial velocity. Looks to me like we've got the pieces for this top height equation. All right. Height, which is 0, is negative 49. Again, different gravity, different equations. T squared plus V0, which is 147, T, plus initial height, which is 0. I'll go ahead and put it here just in case, but it's not actually necessary. So, once again, we have a quadratic. Now, in order to solve this quadratic, we want to attempt to factor it. Again, if you need extra help factoring, let me know. I will absolutely give you more practice on it. Negative 49t squared plus 147t. Now, 147 is actually divisible by 49, so you can pull a 49 out of here, but I didn't expect you to necessarily know that. I do know that I can at least factor out a t from both of these terms. So I'm going to say 0 equals t times negative 49t squared, negative 49t, because I factored out a t, plus 147. Now again, when I have two factors that multiply together to make 0, the way to solve it is to take each individual piece and set it equal to 0. Because if two things multiply together to make 0, regardless of what they are, one or the other of them has to be 0. There are no two non-zero numbers that can multiply together to make 0. So, t equals 0. Again, like I said in the previous problem, it's true, but it's not particularly interesting. At time equals 0, that's the moment when the probe launched the ball. We already knew that it was at height equals 0. That's given to us. No news there. But this one's more interesting. Negative 49t plus 147 equals 0. Subtract 147 from both sides. Divide by negative 49, you end up getting t equals 3 seconds. It takes 3 seconds for the baseball to be launched from the ground all the way up and then come back down and hit the ground again.